So, good morning. Now, myself coming from public research, I was first surprised being asked to give a talk on a rather commercial topic. Still, I think I can provide a personal view and will be interested in what kind of discussion this will trigger. Let me start with something very trivial. Obviously, there is not one supply chain for fusion, but there are quite a number of these. And I'll start with an overview, distinguishing between the general topics that are relevant for all concepts, and then supply chain specific for magnetic fusion, and those that are important for inertial fusion. In general, that is for all concepts, there are a lot of different supply aspects that are related to tritium. I think everybody has understood that by now. And I'll come back to this in a bit more detail later, if time allows. Another general topic is materials. This is partially overlapping with the tritium topic. Still, it has also many other aspects, but this was, I think, largely covered already yesterday. Then, still in the general range, we need energy conversion. And this can basically build upon systems that are available from other power plants, but still they will have to be adapted to the specific fusion conditions. For example, pulsed operation for the tokamak concepts, or specific coolant temperature levels that are prescribed by the materials we have to use. But at least there are synergies with existing solutions we can build upon. Another aspect is remote maintenance and plant logistics for fusion. This also can be based upon adaptation of existing technologies. However, fusion-specific aspects like size and weight of the components, you have to imagine breathing blanket sector will have several cubic meters and can go to up to several tens of tons. Or it's fusion-specific instruments and inventories, radioactive inventories, for example, have to be considered at the right time to set up the supply chain. Then diagnostics already have been mentioned. They are needed everywhere, particularly neutron diagnostics. And then, of course, there are a lot of approach-specific plasma diagnostics. But here, I think a lot of exploratory work still will be needed in the phase of the technology maturation. And only based upon this, supply chains can be established when the concepts and thus the demands will be more clear. Then, specifically for magnet fusion, there are, of course, the magnets, the superconductor and high-temperature superconductor technology with a number of aspects. And here, of course, spin-off and secondary use effects easily can imagine and have already been explained. And there is already a market for such materials and magnets and related technology solutions. And this is, of course, why a lot of startup companies exactly focus on this part of, on this specific supply chain. Then, besides the magnets, magnet fusion needs systems to heat up the plasma. And like for the magnets, this will be a very substantial market. There are several different heating systems. In Europe, the idea is to focus on one of them to limit the plant complexity, and this should be microwave heating. There are other systems, but I will not dwell on this now. Capacities in Europe and worldwide are far away from what would be needed to provide the numbers that would be required to equip more than one demonstration pilot power plant. In my view, these magnet fusion-specific heating systems have little or no impact on other markets. And the same is true for the particle exhaust from magnetically confined plasmas, the so-called diverter. This is a component, I think it was already mentioned. This has to withstand extreme heat loads and also at the same time the impact of neutrons and eventually charged particles. And the system and its specific design is strongly depending on the overall plant concept. However, single technologies like the heat shield materials or bonding technologies could find their way to other fields of application. Now, switching to inertial fusion supplies, I first have to say that I'm, of course, less familiar with these elements than for those of the general and the magnet fusion concepts. What, however, is very obvious, and it also already was mentioned, is the need for extremely powerful, short to extremely short pulse laser systems. And clearly, this technology has a wide range of applications beyond fusion. Inter alia that is why there is now also a huge interest in laser fusion. Here, I suppose that supply chains, can be easily adapted from the production lines of our laser systems. Then, in inertial fusion, there is the issue of the targets. That means you have seen it, the small capsules containing the fusion fuel that will be ignited. The value and market size of these components will depend on how sophisticated these tiny things in the end will have to be, which I find now difficult to predict. So there is quite a range. As the assumption is that about 10 targets, yesterday we had one, but it's in that range, will have to be ignited per second in an inertial fusion power plant. This will require firing systems that enable this, and which precisely inject the targets to the point where the laser beams will hit them. And for the moment, I see this rather as a development task than as a supply chain challenge, but it will become when we know the technological solutions. Okay, now I'll like to dwell a bit more on tritium as far as time allows, and tritium supply means first providing the startup tritium inventory, which has not been covered so far. This will be in a range between a few and 10 kilograms per plant, and tritium is a byproduct in the operation of heavy water fission reactors. Currently, we at KIT obtain small quantities commercially from Canada. Other countries operating such reactors are Romania, South Africa, and South Korea. And one such CANDU type reactor can produce about maybe up to half a kilogram tritium per year. So this can be organized for a small number of pilot fusion reactors if ordered early enough, and of course observing proliferation limitations. Then I would briefly mention that lithium, as already said, consists of two isotopes. Most fusion concepts require an enrichment in the rarer isotope, that is lithium-6, with only 7.5% natural abundance. Then, of course, there is a bunch of tritium processing technology and equipment for separation, purification, storage, accountancy, so far available at laboratory scale, most of them, some at ITER scale, but in any case, scaling up has to be demonstrated before production capacities can be installed. Last not least, the tritium breeding blanket requires specific manufacturing capabilities and technologies that preserve the thermomechanical properties of the material when shaping and bonding them. Okay, then there's, of course, a material supply aspect, which has been largely covered yesterday. And now I briefly want to dwell on how to establish the supply chains needed from my point of view. There's a trivial thing that this supply needs demand. and that means no supply without demand. And by the way, allow me one remark. We quite sometimes hear the expression of a fusion ecosystem. I think this is the wrong view. An ecosystem is something that is stable in itself and rests in itself. This is not what we need in fusion. We need a fast development. There was mentioned the Manhattan Project, the Man in the Moon Project. This is rather what we should look like. And now there is, of course, a mismatch of high expectations and low commitments with respect to the supply chains. And so what could be solutions? Of course, we could have centralized public projects with strong leadership. This worked earlier. This can provide reliability in demand. This is very important. And of course, the drawback is the need for high public investment. We have a lot of private initiatives that can mobilize private capital. The drawback is that this is very heterogeneous and there are no reliable perspectives for the suppliers. A possible solution could be alliances among private initiatives with overlapping interests. Finally, public-private partnership. This is a buzzword now. It is not well defined. It could be a solution if it is set up in a proper way. It's not what I can observe at present, who wants to do what, and then we make a combination. So rather, this has to combine the best aspects from the two worlds. This means still strongly focus on leadership and coherence, and then trigger private investments by granting or accepting limited IP claims. So I think now I have been far above my time slot.
I'm afraid you have, but I loved your last point, so I'm sorry to jump in there, but thank you, Klaus, very much, and we do need to move on, but we'll keep coming back to that and welcome your comments on public-private partnerships. Thank you.